Lesson 2, Unit 5, Example 6, Parts C, D, and E. So Part C, I'm looking at this function sine squared x minus cosine x, and I'm looking at it on a closed interval from 0 to 3 pi over 2. And I know that sine and cosine are both continuous, so the combination of these two functions are going to be continuous. So h of x is continuous on the closed interval from 0 to 3 pi over 2. Okay, so we can use the extreme value theorem like it wants us to. So the first thing we're going to do then is take the derivative. Now remember, this is like the sine of x to the second power. So when we are taking the derivative, we bring the 2 down times sine of x to the 2 minus 1, so to the 1, times the derivative of sine. So that is your derivative, 2 sine x cosine x. And then minus the derivative of cosine is negative sine. So this becomes 2 sine x cosine x plus sine x as our derivative. Now, I'm going to set my derivative equal to 0, and I notice that I can factor a sine out, leaving me with 2 cosine x plus 1. And then that means that either this is 0, so I'm looking for where the sine of x is 0, and I'm also looking for where 2 cosine x plus 1 is 0. So think about where the sine of x is 0. That's at 0 and also pi. Okay, in this interval, it would just be at 0 and pi. And then we're going to take that 2 cosine x, subtract 1 from both sides, divide by 2 on both sides. And so we're looking for where the cosine of x is negative 1/2. Well, we know that cosine is negative in the second and the third quadrant. Okay, so this would be a negative 1, and this would be a 2. And so that makes this a square root of 3 and a negative square root of 3. So therefore, my reference angle there is going to be pi over 3. So it's not just pi over 3, though, because it's in the second quadrant. Like here's 1 pi over 3. So this is actually going to be 2 pi over 3. And then it happens again. Here's 3 pi over 3. That would be pi, which would be 3 pi over 3. So this also is at 4 pi over 3, the next 60-degree angle there. Okay? So we've got 4 of these points that are in between our endpoints. So on our candidates test, see if I can fit them all on here. We've got x equals 0, which actually that is an endpoint. And then the next one would be 2 pi over 3, and then pi, and then 4 pi over 3, and then 3 pi over 2. Okay, and so, or this would actually be h. And so if you get that in your calculator, you'll see that you have negative 1 at 0. You've got 1.25 at 2 pi over 3. You've got 1 at pi. You've got 1.25 at 4 pi over 3. And you've got 1 at 3 pi over 2. So you have an absolute max of 1.25 at x equals 2 pi over 3 and x equals 4 pi over 3. And you have an absolute min of negative 1 at x equals 0. Okay, so that would be for part C. And then on part D, there is a problem, okay? if I had to think about what the domain of this function is, I would be thinking, well, the x squared minus 9 can't be negative and it can't be 0. Okay, so it would have to be greater than 0. And so that means that x squared has to be greater than 9. And so, like, if think about that. If x squared had to be greater than 9, like if I can't put a 0 in, I can't put a 1 in, I can't put a 2 in. So you're talking about all the numbers less than -3 and all the numbers greater than 3. So this is a disjunction. So your domain, your domain is -infinity to -3 union +3 to infinity, okay? And so look at what your closed interval is. There is a problem because in between -3 and 3, your function is not defined at all. So f of x is not continuous on -2, 5. Since the domain of f of x is undefined on -3, 3. So the extreme value theorem does not apply. Okay? And then for part E, if I'm thinking about this, and I can look at this in my calculator just to make sure, and when I look at this function, h of x is continuous for all reals. Because I don't have to worry, because it's a cube root, I don't have to worry about negatives underneath the root or anything like that. And so now I'm going to go straight to taking that derivative. So I bring the 1/3 down times x minus 2 squared. Let me put that in a bracket. To the 1/3 minus 3/3, which is going to be -2/3. And then times the derivative. Well, the derivative of that, I'd bring the 2 down times x minus 2 to the 1, and then times the derivative of x minus 2. So this gives me 2 times x minus 2 in the numerator, and 3 times x minus 2 to the 4/3. I almost said -4/3. So it would be -4/3 up here, but when I bring it down, it's +4/3. Now, since this x minus 2 is, if you don't mind me saying, is like to the 3/3, this is going to reduce because this is, this is going to cancel with 3/3 of this one, right? And so this becomes 2 over 3 times x minus 2 to the 1/3. And so that's your simplified derivative. And so if I set that equal to 0, nothing is going to make that 0 because whatever makes the numerator 0 will make it 0. And 2 cannot be 0. So there's going to be nothing will make it 0. Okay? No values of x will make it 0, but we could look to see what makes it undefined. And so if x is 2, then h prime of x is undefined. So x equals 2 is a critical number. So on our candidates test, not only do we have our endpoint of 1, we've got our critical number of 2, and we've got our endpoint of 10. And so if I put a 1 in, I get 1. If I put a 2 in, I get 0. If I put a 10 in, I get 4. So this gives me an absolute max of 4 at x equals 10 and an absolute min of 0 at x equals 2. Okay, so that's using your extreme value theorem. Okay, so by the extreme value theorem. All right, I think that was it. I hope that helps. Thank you.